My name is Maila Hallare. I'm an assistant professor at the Department of Mathematical Sciences, United States Air Force Academy, and this is my Simayodi Expo 2023 presentation. I would like to thank Professor Brian Winkle and the organizers of the Simayodi Expo 2023 for allowing me to share my work. The title of my talk is Battle of the Smartphones, Will One Drive the Other to Extinction? Before I present my work, I would like to promote the CODI Journal. CODI is the acronym for the Community of Differential Equations Educators, and we maintain a journal that publishes academic work that promote the teaching and learning of differential equations. This year, 2023, we launched a special issue, and the theme is Engaging the World. Differential equations influence public policy. The deadline to submit proposals has been recently extended to March 15, 2023. For any questions about submitting your proposals or even how your existing ideas on differential equations may fit the theme of our special issue, please do not hesitate to contact me through my email address, maila.halyare@afacademy.af.edu, or Dr. Samer Habre, who will serve as the editor for this special issue. So these are the important dates for this special issue. So for this special issue, we reflect on questions such as how do we describe public policies quantitatively, and how do we embed these descriptions into differential equations? How do we measure the effectiveness or adjust public policies to fit a desired purpose? And how do we develop mathematical fluency among our students when discussing mathematics and public policies? So please consider submitting your work to the CODI 2023 special issue. Thank you so much. Okay, so this is the abstract of my talk. The BAS model is a first-order nonlinear differential equation that models the diffusion of a product or an innovation using parameters that capture the market's spontaneous innovation and imitation. Created in 1969, not 1979, by Frank Bass, this model is still currently being used in sales forecasting and in making management decisions on pricing and advertising. In this talk, we create a two-dimensional system of differential equations with the Bass model in the growth component, and with interaction terms that capture competition between two products. The resulting system is then used to analyze the interaction between the top two smartphone brands. In particular, we would like to know if the mathematical ecology result called competitive exclusion principle applies to the resulting system. Competitive exclusion principle predicts that there is a state wherein one product may drive the competition to extinction. So the top two smartphone brands that we consider here are the Apple and Samsung smartphone brands. This is a short memoriam for Dr. Frank Bass, who is often called the father of marketing science. He served as a professor of marketing science at the University of Texas at Dallas. His original paper on the Bass model was recognized as as one of the top 10 most influential papers in the history of management science. So this is the Bass model. It is a first-order two-parameter ordinary differential equation where F is the fraction of the population who have adopted an innovation or technology. P is the parameter that captures spontaneous innovation, and Q is the parameter that captures the imitation of the innovation. These two parameters are assumed to be positive and less than 1, with P less than Q yielding the more interesting scenario. This graph shows profiles of the function f with different parameter values for P and Q. In particular, look at the graphs where P is less than Q, represented here by graphs marked with a diamond and with X. We see a characteristic S-shaped curve for these two graphs from 0% adoption to 100% adoption of a certain innovation, and there is a point of inflection somewhere in the middle. For parameter values where P is greater than Q, this point of inflection is not in the first quadrant. In my research looking at the marketing science books, this point of inflection is quite important in making business, marketing, and management decisions for the products for the products that a company is trying to sell. So as we know in calculus, this point the point of inflection tells us that the function the speed of the speed of the innovation is increasing prior to the point of inflection, and it is decreasing after the point of inflection. Okay, so again, this is the Boss model, and undergraduates are able to do simple analysis for this equation right from the start or during the first few weeks of an ordinary differential equations class. For example, using the separation technique with partial fraction decomposition, they can compute the closed form solution of this equation. As we have seen before, these are some of the properties of f. It is positive, non-decreasing. It has an S-shaped curve and it has a point of inflection. Note that P is less than Q. Okay, so about 2 years ago, I worked with one of my classmates in graduate school on a Simayodi project that uses the Boss model to study the technology adoption in the US. If you visit this website here, ourworldindata.org, you will be able to see graphs such as these. You will be able to, or you can download the data using as a CSV or as an Excel file. The website Our World in Data has many other interesting information and data that can be used in a differential equations course. For our Simayodi project, which we titled The Flush Toilet Slow and Late Start, we presented a guided activity on analyzing data on the adoption of the flush toilet, which according to history.com, the first flushable toilet was actually invented in the 1590s in England by a godson of Queen Elizabeth I. But just recently, CNN reported that archaeologists in China have found the remains of what could be the oldest flush toilet. Well, anyway, like most innovations in the 19th and 20th century, only the elites of the society have access to this technology. So in 1860, we see here on the table that about 1% of the US household had flush toilets. And more than 100 years after, in 1989, according to ourworldindata.org, 100% of the US households have flush toilets. So the Boss model computes that the coefficient or the parameter of innovation is quite low, 0.00051, and the coefficient of innovation is 0.06. These parameters were obtained by using the solver capability in Excel, where the objective, where we designed the objective to be finding the parameter values such that the squares of the errors are minimized. So by the error, I mean the error between the given data and the computed data using the Boss model. As we can see here on the right, the orange graph obtained by using the best fit parameters for F is a good fit to the actual data for this problem. So here I am also sharing how to do the same process of computing the best P and the best Q using RStudio. If Excel has the solver capability, RStudio has the fit model. Well, this is using the Julia. For more information, you can look at our Simayodi project on the flush toilet. Okay, so based on my experience, I recommend the following. During the first few week of classes in the first course in ODE, motivate the power of ODE as a modeling tool. And some output and some feedback that I would like to share are, when I did this in my ODE class, I see that there was a better understanding of the role of parameters in an ODE. For some students, they previously I noticed that some of them take weeks to understand the difference between variables and parameters. The BOSS model is a good example to be used in class because it is highly accessible and it does not need a lot of background in physics, bio, or chem, or math. So students develop a sense of belonging because they understand the example right from the start. So now moving on to um, our model. So here we see a competition model that has the BOSS model for the growth. So in both the first and second equation, we see the BOSS model in the first term. This is the BOSS model for the adoption of X, of brand X, and this is the BOSS model for the adoption of brand Y. For the second terms of both the first and second equation, we include the so-called competition. The minus sign here tells us that the interaction between X and Y is competitive in nature. So we can think of the Apple, or we can assume that X is for the Apple brand and Y is for the Samsung brand. A summary of the parameters are given in the table, where this time we include new parameters M1 and M2 for the market potential for product X and Y respectively. So here, A and B are the competition parameters. Because M1 and M2 are market potentials, this time, unlike the original formulation of BOSS, the X and Y will be the raw numbers of the adopters, not just fractions of the population. So remember, A and B are the competition parameters. So the inspiration for this project came from a journal that I found, came from a paper that I found in the International Journal of Trade, Economics, and Finance, published in 2018. The title of the paper is Diffusion Model for the Adoption of Smartphone Brands Under Competitive Pricing. In this paper, the authors computed the values for the parameters M, P, and Q for the Apple and Samsung brand. They also created new models that capture the sensitivity of the market, and this is through the parameter gamma. And so in this paper, they used statistics methods, basically regression methods to compute the parameters M, P, and Q. They did not look at the dynamic interaction between the two brands over time. So in this project, what I did was I created a differential equation system to capture the competition between Apple and Samsung. So let us look at the mathematical ecology result called competitive exclusion principle, which can be summarized as the 4 C's. Complete competitors cannot coexist. So we ask, in the smartphone market where Apple and Samsung are the top 2 brands, will one drive the other to extinction? First, let us review the 4 C's in the special case of the so-called Lotka-Volterra competitive system. And the equations look like this. So here we see species N1 and species N2, both of which are growing logistically with carrying capacity K1 and K2. On the right-hand side, we see the null-Klein analysis for this system. So for the null-Klein analysis, we see the null-Kleins, the steady states, and some representative solutions of the system, as you can see here with the arrows. So in some cases, like most ODEs, like the Lotka-Volterra competitive system, complete pictures of the solutions can be established by considering a null-Klein analysis. In some cases, of course, the null-Klein analysis is not sufficient to say statements about the dynamic behavior of the system. So in this case, most of the time we do a linearized we study the linearized behavior of the system for points close to the steady state. Okay, so this is the Lotka-Volterra competition system. This would be the analysis for the four cases. And let us do a dimensionless, let's do some scaling and consider the dimensionless system. So, for the competitive exclusion principle analysis, we proceed as follows. So in case one, we see that the coexistence equilibrium P is stable. That would be this point where the two null clines intersect. So if the interspecific competition, if the interspecific competition parameter is not too strong, A12 and A21 are both less than 1, then the two species can coexist in a stable way. So actually, if you do further analysis, you can say that although the species may coexist, the price that they pay for competing with each other is that they do not reach the density that they would have achieved if the other species were absent, otherwise known as the carrying capacity. So stable coexistence, but not to the full potential of each species. For case two, the interspecific competition is aggressive. So A12 greater than 1, A21 is greater than 1 also. And ultimately, one population wins. So it could be so the solution trajectories may either go to this equilibrium, boundary equilibrium point, or this equilibrium point. The winner depends on the initial conditions, or whichever has the starting advantage. Now let us look at case 3 and case 4. So the interspecific competition of one species, in this case, dominates the other. So A12 is less than 1, and A21 is greater than 1 for case 3. And then for case 4, we reverse these inequalities. It can be shown that in either case 3 or case 4, this stable node is globally stable. This stable node is also globally stable. And so the species with the strongest or with the stronger competition will always drive the other to extinction. And we say extinction because in this case, for example, case 4, the x or the n1 coordinate is 0. In this case, the n2 coordinate is 0, and hence we say that the species become extinct. Now, we would like to investigate the competition between Apple and Samsung using this lens called competitive exclusion principle. First, let us look at the equilibria. So we set each of the equation equal to 0. So in the end, it turns out that the equilibria will be the roots of a fourth degree polynomial in X. So one of the roots in this fourth degree polynomial is always X equals M1, and the other three roots will come from this cubic polynomial whose coefficients are given on the screen, A, B, C, D, and you will see the interaction between the parameters P1, Q1, M1, P2, Q2, M2, and the competitive parameters or competition parameters A and B. So if we look at the discriminant of this cubic polynomial, then we can have an existence result on the for three real roots of the cubic polynomial. So we can consider two cases from this analysis. Either there are two real roots for the fourth degree polynomial, x equals m1 is always a root, and the other one is a negative root and a pair of complex conjugates, or the second case wherein all four roots are real numbers. Or all four roots of the fourth degree polynomial are real numbers. Now, let's proceed to the null-Klein analysis. For the null-Klein analysis, we simply set each of the equation equal to 0. In this case, the x and y null-Kleins are both hyperbolas. Unlike the Lotka-Volterra competition model that we have seen earlier, where we had lines only. So the asymptotes for these null-Kleins are displayed on the screen. So in the first case, wherein we have we're in the um, fourth degree polynomial for the equilibria has two real roots only. Let us look at the null-Klein hyperbolas. The x null-Klein hyperbola is given in brown, where the broken lines are the asymptotes. The y null-Klein hyperbola is in red. Again, the red dotted lines are the asymptotes. Where the brown and the red null-Kleins intersect, we have our coexistence equilibrium. So we would like to ask now, is this coexistence equilibrium between the Apple and Samsung brand a stable equilibrium point? And so for this, we will apply the Jacobian technique. So we can compute the Jacobian at the point M1, M2, analyze the trace and determinant, and we will use this standard result on two-dimensional systems. So the picture is given here. So if the trace is negative and the determinant is positive, we say that the coexistence equilibrium is stable. So in our case, using the parameters computed by the authors, then we say that our coexistence equilibrium M1, M2 is stable if and only if the product of the coefficient parameters is less than 0.0177, because the trace is always negative. Okay, so now let us look again at our case one, wherein we have four roots for the equilibrium equation, and hence we have case one wherein we have two real roots for the equilibrium equation. Okay, so we were asking whether this coexistence point is a stable point, and using the analysis, using the determinant analysis, we can compute, or we can verify that this coexistence equilibrium is stable because AB is less than 0.0177 in this case. Okay, and what's the interpretation? The Apple and Samsung brands can coexist stably. Now let's proceed to the second case, this time wherein we have four real roots. The four real roots are M1, a negative root. So the intersection between the null-Kleins is on this side, which is irrelevant in our situation, and two positive roots. So we have 1, 2, and 3 positive real roots. So like before, we have the brown null-Klein, which is the X null-Klein, and the red null-Klein, which is the Y null-Klein. And the two null-Kleins will intersect at these 3 points. So for these 3 points, let us label them S, E, A, wherein S will have a very small X component and a very big Y component. A will have a very big X component and very small Y component. And E is the coexistence equilibrium point. Okay, so according to our analysis using the determinant, if AB is less than 0.0177, then the coexistence equilibrium is stable. Okay, we can also do a null-Klein analysis for in this case. So using the null-Klein analysis, we are able to see that S is unstable and A is also unstable, and that E is stable. We can also look at the so-called Bend-Dixon criteria, because it could be that there are periodic orbits on this side, but computing the divergence of F, we can verify that there are no periodic orbits. So in the case that AB is less than 0.0177, then this coexistence equilibrium is stable. In this case, Apple and Samsung coexist. What kind of stability? Well, it depends on the parameter values. So for case 2.2, if AB is greater than 0.0177, then this time the coexistence equilibrium is saddle. So one of the brands wins the competition. Will it be the Samsung or the Apple brand? So even though one of the brands will win the competition, it will not drive the other to extinction. So who wins? Well, it depends on the basin of attraction of the system. For example, if the initial point is somewhere there or there or there, then the Apple brand wins. However, if the initial condition is somewhere there or there or there or there, then the Samsung brand wins. So a bifurcation analysis can be obtained by looking at the equilibria, by looking at the stability of our points. For some details on this, please watch out for my cadets poster and paper on this topic. Thank you so much for your attention. Bye-bye.